Welcome to this explainer. Right now, we are literally standing at the edge of a massive, critical engineering paradigm shift in computing hardware. For decades, the entire foundation of our digital world has been built on just one predictable premise: shrinking silicon electronics. But, well, physics is finally catching up with us. Today, we're going to explore the post-Moore era, look at the physical limits that are actively breaking modern electronic architectures, and dive into a fascinating, fundamentally different approach that engineers are looking toward to solve this impending crisis. I'm talking about optical computing. Let's kick things off with a number that perfectly defines the crisis we're facing: 300,000. To really understand why we absolutely need a paradigm shift, we have to look at this staggering explosion in computational demand. Between 2012 and 2018 alone, the computational power required to train the largest artificial intelligence models didn't just double or even triple, it increased by a factor of 300,000. To put that into perspective, the contrast here is just wild. Over that exact same period where AI compute demand skyrocketed by 300,000 times, the old, reliable engine of the tech industry, Moore's Law, would have given us only about a 7 times enhancement in performance. This desperate discrepancy, this massive computing hunger, is stretching our current hardware to its absolute breaking point. We're simply asking silicon to do way more than it physically can. So to navigate this crisis today, here is our roadmap. First, we'll look at the end of Moore's Law. Second, the optical computing solution. Third, the conversion energy bottleneck. Fourth, the analog precision problem. And finally, navigating the hybrid future. Alright, diving right into Section 1, the end of Moore's Law and its physical limits. Why exactly are modern electronic computing architectures failing to keep up? Well, for the longest time, we relied on something called Dennard scaling. Basically, this was the rule that as you shrink a transistor down, its power density stays constant. That meant you could run it faster without completely melting the chip. But as we've pushed CMOS technology further and further, Dennard scaling has actually failed. Those tiny shrunk transistors can no longer maintain that constant energy density. And that leads us straight into what engineers call the heat wall. If we try to push CPU clock speeds past roughly 5 GHz, the thermal effects from power dissipation become a massive bottleneck. The chips literally just get too hot to function. And honestly, the problems get even weirder as we get smaller. When we try to shrink transistor gate channels below the 5nm node, we aren't just fighting heat anymore. We start fighting fundamental quantum physics. Below 5 nanometers, we see the emergence of highly unpredictable quantum effects. Electrons actually start exhibiting quantum tunneling, which is essentially teleporting through barriers and completely disrupting strict digital logic. On top of that, we see quantum scattering, which drastically reduces efficiency. Bottom line, we can no longer just shrink our way out of this problem. Which brings us to Section 2, the optical computing solution. If pushing electrons through tiny silicon wires is generating too much heat and triggering quantum errors, what's the alternative? Light. Now, the crucial thing to understand here is that optical computing isn't just faster electronics. It is a structurally completely different medium. Instead of relying on this sequential, heat-generating flow of electrons representing strict ones and zeros, optical computing processes information using the physical characteristics of continuous light waves, like amplitude and phase. And because it relies on near dissipationless dynamics, optical computing generates virtually zero heat during the actual calculation. Plus, since different wavelengths of light don't interfere with each other, optics offer this massive intrinsic parallelism. Just look at the sheer elegance of a 2-lens 4F system. Imagine light simply propagating through the first lens. As it does, it undergoes a complex mathematical Fourier transform, instantly, literally at the speed of light. Then, as it passes through a scattering medium and the second lens, it performs a mathematical convolution on that input light. As long as there's no optical loss from the lenses themselves, this entire highly complex calculation happens without any energy loss. The computation occurs simply by letting the light travel through space. It's brilliant. Sounds like a magic bullet, right? Well, let's step back from the hype for a second and look at Section 3, the conversion energy bottleneck. Let's talk about the main engineering complication preventing optical computers from immediately replacing your current laptop. There is a major snag here, and it's all about input and output costs. If your data starts in a standard electronic memory, it has to go through quite a journey. First, it leaves electronic memory and hits a digital-to-analog converter, or DAC, to become an optical signal. Then the optical compute happens, and remember, that part is nearly free. But to actually read the answer, That light must hit a photodetector and go through an analog to digital converter, or ADC, to go back into electronic memory. This transduction process costs a massive amount of energy and it's severely bandwidth limited. If engineers aren't incredibly careful, the power tax of these converters will completely erase all the energy benefits you got from the optical calculation in the first place. And the conversion cost isn't the only hurdle. That brings us to Section 4, the analog precision problem and algorithmic limits. You see, optical systems are analog systems. They deal in continuous waves, not strict discrete ones and zeros. As Peter L. McMahon noted, it is difficult to achieve an effective precision greater than 10 bits in any analog computer, including analog optical computers. Because light is subject to systemic errors, crosstalk, and random thermal noise, you simply cannot guarantee the absolute pixel-perfect precision that a traditional digital electronic system gives you. So what does this actually mean for us? Well, it means general-purpose Boolean logic algorithms, the exact kind that run your spreadsheets in your operating systems, are extremely difficult to seamlessly map onto optical operators. We expect general-purpose processors to be entirely error-free. If an accountant adds two numbers together, the sum has to be perfectly exact, not some continuous noisy approximation, right? Therefore, trying to build a general-purpose processor to replace your CPU entirely with optics still remains largely out of reach. So, where does all of this leave us? Let's wrap things up with Section 5, navigating the hybrid future of optics plus electronics. The realistic takeaway here is that the future is not about optics entirely replacing electronics. Instead, we're looking at a highly strategic hybrid integration. We are going to see optics used as special-purpose analog coprocessors, specifically targeting tasks like highly parallel matrix vector multiplications. Remember that massive AI computing hunger we talked about earlier? Well, no, that works, especially during the inference phase, are intrinsically resilient to noise. They don't actually need perfect precision. An 8-bit equivalent works just fine. And by designing hardware and software together, we can process massive batches of data at once. By doing computations with a complexity of n squared or n cubed, we can essentially amortize that heavy energy cost of the digital to analog converters. This makes the whole hybrid system vastly more efficient than electronics alone. So the physical hurdles of heat and quantum limits have totally forced us to look beyond the silicon transistor, and light really does offer this beautifully elegant near-zero heat alternative. But bridging the gap between error-prone, continuous analog waves and our strict digital electronic world remains the absolute ultimate engineering challenge of our time. Will we one day see light completely replace traditional logic, or are we destined for a permanently hybrid reality where electrons manage the memory and photons just do the heavy lifting? It is a fascinating post-Moore horizon out there, and understanding these physical dynamics is exactly how we'll see where technology goes next. Thanks for joining me on this explainer, and keep your eyes on the speed of light.